Okay, well, welcome to our October Statmos seminar. Today we've got Michael Scheuerer, who's currently at NOAA and ESRL, Physical Sciences Division. He got his PhD in mathematics in Göttingen in October of 2009, and then after that he was doing a postdoc at Heidelberg. Um, and the reason, partly, for getting this here is I've had quite a few questions about people who want to know more about how we evaluate predictive performance. And Michael's an expert of this, and he's got a talk here that hopefully will help us think a bit more about when we make predictions, how we can actually say they're good, bad, or indifferent, I guess. So thanks a lot, Michael.
Thank you very much, and good morning, everyone. As Peter said, this is a seminar talk about evaluating predictive performance, and it's going to be relatively general and basic in terms of the mathematics. So you'll probably not see a lot of mathematics that you haven't seen before, but I would assume that with many of these things, you might not have been aware how useful they are, how important they are, and sometimes how dangerous they can be if they are applied carelessly. Um, and this is what this talk is mainly about. Um, so first of all, let me give you a little bit of motivation why you should even care about forecasting theory, which sounds like something very special. If you hear forecasting, you probably think about something like a time series or something that we observe for a while, and then we want to make predictions to the future and want to say what the future is going to be. Those of you who have come in touch with geostatistics know that every question that we can ask about time also translates somehow into space. So the spatial setting would then be that we observe a quantity at a couple of locations in space. And then again, we want to make predictions at locations where we do not have measurements. But it's not only those fields, but even very basic and very general things like regression can be viewed from a, a probabilistic forecasting perspective. So this is a regression setup, and I'm back to the first example here where we are trying to predict ozone levels. But here the approach is that we may have some covariate that it's easier to predict, like temperature, and then we want to identify a relation between our covariate temperature and ozone, and want to use this to make a prediction. And in all these three examples, since we are statisticians, we're not only interested in the point prediction, but what we usually do is we make some distribution assumption, very often normal distribution, but not necessarily. It can be very fancy distribution assumptions. But once we've done that, statistical theory usually gives us a whole distributional forecast. And this is exactly how we view things in probabilistic forecasting theory. We think that the appropriate way of viewing forecasting is not giving just one point, but a whole distribution, which tells us something about prediction uncertainty and which permits us also to derive things like confidence intervals, probabilities of exceeding a certain threshold, and so on. So this is the point of view that I'm going to adopt for the rest of the talk, that the object that we issue as a prediction is an entire distribution. And as a final example, I want to mention Bayesian statistics, because for Bayesians, this point of view should be something very natural, because whatever Bayesian people do, they always end up with a posterior distribution. Even if they only fit the model and want to identify parameters, the result is always a distribution. And then we can again ask the same questions, whether this distribution is biased, whether it adequately reflects the uncertainty, and so on. So this is just yet another example where the object that we end up with is a predictive distribution. And the rest of the talk is dedicated to the topic of how do we judge the value of distribution. And to do that, we first have to formalize this notion of what a good forecast even is. For a point prediction, this is sort of obvious. If we have a point prediction, then a good point prediction would somehow be close to the truth. But for a distribution, this is not quite as obvious. And there's a paper by Gneiting et al., where they have tried to formalize notions that are quite intuitive and try to put them into a mathematical framework that allows us to look at these things in a more rigorous way. And in this paper, they contend that the goal of probabilistic forecasting should be the maximization of sharpness subject to calibration. So there's now two different notions here that I have to explain. The easier one is sharpness. Sharpness means that our predictive distribution should be very specific, very concentrated. But this only makes sense if it is still consistent with what we observe. And I want to illustrate this in a simple example with one step ahead predictions of an AR1 process. So in this plot, the red line is a AR1 process that I have simulated, and I'm now looking at different forecasters that produce one step ahead probabilistic predictions. And one very specific aspect of this is a prediction interval, and I'm just displaying 80% prediction intervals. Again, this is a very this is only one aspect of these notions of calibration and sharpness, but this permits to illustrate what these two different notions are about. So my first forecaster is actually quite skilled. He knows the process, and the uncertainty that is left is just the randomness, the driving noise of this process. And in this example, sharpness would mean that his prediction intervals are as small as possible. So the width should be as small as possible. Calibration here would mean that the empirical coverage is close to the 80% nominal coverage. And looking at this picture, we would probably agree that this is the case here, or we have no reason to assume that there is something completely wrong. So this is a forecaster who is reasonably sharp and is also calibrated. Here's yet another forecaster. And this forecaster is less skilled, and we can see that his prediction intervals are much wider. But this forecaster is aware of his reduced skill, and he adjusts this by increasing the uncertainty. So he's less sharp, but he's still calibrated. He again matches the 80% nominal coverage, and so we have a calibrated forecaster. The final forecaster is again more skilled. His point predictions are rather accurate, but he's somehow too self-confident. He's extremely sharp, which is normally something where we would say this is a good thing, but he's not calibrated. His predictions intervals are not consistent with the verifying observation. And so in that sense, he's still a less skilled forecaster than the first one, because he does not give appropriate assessment of his uncertainty. So these are the two notions of calibration and sharpness. And well, as far as sharpness is concerned, looking at prediction intervals is indeed already a very good tool to say how sharp a forecaster is. For calibration, things are a little more complicated, and I want to show you another tool that is quite useful. And this is one of these examples where I'm showing you something that's extremely simple, but in my opinion, extremely useful. And this is the so-called probability integral transform. So the situation that we have in mind here is that we have a whole bunch of predictive distributions, here given in the form of a CDF, and we have verifying observations. And then a useful thing to do is to evaluate all these predictive cumulative distribution functions at the verifying observation. And the particular notion of calibration that we consider here is called probabilistic calibration. And probabilistic calibration means that if we consider draws from the unknown truth, so we draw the observation from the unknown true distribution, then these are statistically not distinguishable from draws from the forecast distribution. So this is the hypothesis, and if this is true, we speak of a probabilistic calibrated distribution. And then under this probabilistic calibration, this PIT value is simply or should follow a uniform distribution. This is very basic statistical theory, but it is very useful because this is something that we can easily assess by just plotting a histogram of all these different PIT values. And then studying this histogram tells us a lot about what is potentially going wrong with our predictions. And one reason why this is so useful is that often in statistics, or to do statistics, we need to aggregate over a whole lot of different cases to get something that's statistically meaningful. And very often we need that these are identical or even independent. And as we're talking about predictive distributions, and we think about the situation where we produce a different forecast every day, then those are definitely not going to be identical. So there is no obvious way to aggregate over the different distributions, and there's also normally not a reasonable way to aggregate over the observations. But if we make this transformation, then we transform to something that always has the same distribution, and it makes sense to aggregate over the PITs. So here's just a few examples how studying those histograms of PIT values can help us identify shortcomings of our forecasting mechanism. The simplest is an under or over forecasting bias. So if we are under forecasting the truth, then the observation will very often lie in the upper tail of our forecast distribution, and we get this triangular shaped PIT histogram. So this shows us that our forecasts are systematically biased. And this is something very simple that we could have identified by just looking at the errors. The nice thing about the PIT histogram is that we can identify more complicated things and can look at higher moments. So as we go to the second moment, we have here examples for under-dispersive and over-dispersive forecast. So if the representation of uncertainty is inappropriate and we're sort of too self-confident about the accuracy, then our histogram would look like the one on the left. And if even too much uncertainty is claimed, then it would look like the one on the right. Now we can move on to even higher moments. Here's an example where the skew of the forecast distribution is wrong. And then it gets more and more complicated to interpret these, but we can still take a look and we can see that it makes sense. So if you look at this thing here, if our forecast distribution is left skewed, then what we typically observe is that too many observations fall into the highest bin of the histogram, although overall the uncertainty seems adequate, but the shape of the histogram is wrong and indicates a skew. And conversely, for the right skewness. And finally, for the kurtosis, where it gets more and more complicated to distinguish systematic effects from sampling variability, but you can again see that if the tails are too light, then we have too many observations here in the bins, in the lowest and the highest bins, and conversely, if the tails are too heavy, then there's too few observations falling into those bins. So these PIT histograms are really useful and can tell us a lot about systematic problems or issues with our forecast distribution. Now this is a very useful diagnostic tool, but sometimes we want to compare the performance of different forecasters, and then it's probably a bit difficult to just look at a couple of pictures and telling based on the pictures who's doing a better job. And so I want to talk about another tool, which is the so-called scoring rules, and this is a more quantitative measure of performance. Scoring rule is simply a function that assigns to our predictive distribution and the verifying observations a numerical value. And we take scoring rules to be negatively oriented. And so this means we want this value to be very low. Low values would tell us that this is a very good forecast in comparison to higher values. There is one important property, because like this definition is very general, we could come up with all sorts of scoring rules, but one property that we would like our scoring rules to have is this property of being a proper scoring rule. And this essentially means if our observation is a draw from a distribution G, then using this distribution G as our forecast gives us the best score. And this is this seems very obvious, but people have used scoring rules that are not proper, and using a non-proper scoring rule essentially means that even if I know the correct or the best possible forecast distribution, I might be encouraged to quote a different distribution because I know that the other distribution is going to give me a better score. I'm going to be rewarded for a not honest prediction. But if our scoring rule has the property of being a proper scoring rule, then I'm encouraged to quote my honest belief. And well, there's this notion of being proper, and there's also the notion of being strictly proper, which essentially means that that this is a strict inequality. So quoting the true distribution gives strictly the best scores. Here's a few examples. The example that you probably know, even possibly from another context, is the so-called logarithmic score. And this is essentially the negative log likelihood if our predictive distribution has a density. And you will realize that there is a close connection between what you already know from estimation theory and probabilistic forecasting. When you do parameter estimation, then the idea of maximum likelihood is that you choose your parameters in such a way that the distribution that comes with these parameters is most consistent with the observation. And in probabilistic forecasting, we have exactly the same situation, apart from the fact that the parameters are already fixed, but the score still tells us how consistent our forecast is with what we finally observe. Here's another example of a very popular score, the so-called continuous ranked probability score. And you see that this is essentially the integral over two different cumulative distribution functions, if you want to say so. This is just the CDF of our forecast distribution. And you can view this part, sorry, I forgot the pointer, and you can view this part here sort of as the empirical CDF of a single observation only. And we also have a different representation of this CRPS, which is given here. And in here you can see that the CRPS generalizes the mean absolute error or the absolute error that we use for point forecasts. Because if our predicted distribution is a Dirac measure, then this part here just goes away, and this part simply becomes the absolute error. So this is another nice property of the CRPS. I want to illustrate these methods that I've just described on an example. And I apologize here because what you're going to see on the next slide is a really poor statistical modeling. And my excuse is that I don't want to talk about a fancy statistical model. I want to use my time for talking about how to verify the quality of this model. So let's do some exploratory analysis first. You see here a time series of SO2 concentrations, and you see that this is pretty skewed. So let's take a look at the log observations. You see it's actually still skewed, which is part of why this is a really difficult prediction problem, and probably also a good reason for not doing it the way that I will do it, by a rather simple-minded time series approach. But let's do it anyway. And let's next take a look at the autocorrelation function and the partial autocorrelation function of this log series. And you see things are even worse. There's very little autocorrelation. So essentially, these plots tell us that making predictions on a time series basis is going to be really hard. And so here's my simple-minded model. I don't want to model the logs, but I want to model the values on the original scale. And I'm using therefore a Fréchet distribution because this is a distribution that permits highly skewed and heavy-tailed predictions. And it has two parameters. One is a shape parameter that I will estimate, but I will assume fixed over the whole forecast or verification period. And it also has a scale parameter, and I will try to model this scale parameter with a very simple time series approach. I will consider two different models here. Model 1 simply studies a seasonal cycle. So if we would go back here, we can sort of guess that there is some seasonality in those SO2 concentrations. And my first model only exploits this seasonality. So it takes this scale parameter as an offset plus a seasonal component. And model 2 is slightly more sophisticated. It also takes this seasonal part as sort of an offset, but then it also tries to make use of the little autocorrelation that is there, and has an additional parameter that weights the seasonal part, but also uses the value that we observed on the preceding day as an input for our model. And now I estimate all these parameters by maximum likelihood, and then this is what I get for my scale parameter. The black curve shows the seasonality of the scale parameter, so we can see that there's indeed some seasonal difference. And the red curve corresponds to the scale parameter of my predicted distribution using the second model that uses the information of the preceding day. And I'm gonna use all these verification tools that I've shown you before to assess the fits of the two different models. So let's first take a look at those histograms. We see that they're not entirely flat as we would wish, but at least we see that our model is, although it's very simple, is set up such that there is no systematic bias, and the overall uncertainty is represented more or less okay. We see that the problems here are really with the higher moments. So it's essentially the fourth moment, the kurtosis, that is completely inappropriate. If you compare to what I've shown you above, you would see that actually both tails are too light. This is what those histograms would tell us. This is somehow surprising because even the lower tail is too light. But that seems to suggest that maybe starting our predicted distribution at 0 is not quite appropriate. So we could spend some more time to study these and try to figure out how we could improve our statistical model so that these two histograms become flatter and give us better distributions. Overall, it's probably fair to say that the predictions or the predictive distributions are not too bad. But please remember that this is only calibration. Even if they were completely flat, that would say nothing about how useful they are, because we've already seen that those predictive distributions will probably be not very sharp, because we just have very few information in this time series that we can exploit. So let's now take a look at those more quantitative measures and see what this tells us about the ranking of the two models. And looking at this log score and the CRPS, we see that indeed the more sophisticated model gets better scores, but we see that the difference is really small. So the conclusion from these scores would be that that very little information that contained in the time series can be leveraged to get better predictions. Or it can just tell us that my statistical model is very poor. But this is the way how you would look at those predictions and how you would assess them and study the shortcomings of the different models. If you take a look at the prediction intervals, you can see again what we already saw from the histograms, that the coverage at the intermediate level is too low, while the coverage at the higher levels is even too high. And this just confirms the issues about the wrong kurtosis that we have seen before. Let me move on to the next topic, which is going back to the topic of point forecasts. I tried to convince you at the beginning of the talk that a statistician's perspective should be to always communicate the uncertainty and to view forecasts as probabilistic and view forecasts as giving a whole predictive distributions. But sometimes we are required to condense these entire distributions back into point forecasts because this is sometimes necessary for decision making, and people want like a simple quantity rather than a whole distribution, which is harder to deal with. And then the question is, how do we get there? If we still do our statistical modeling and come up with some fancy forecast distributions, how do we get back a point forecast? So we could, for example, use the mean or the median if we want to quote something as our best prediction. And the question is, what specifically should we use? And the second issue is, I said at the beginning that it's sort of clear what a good prediction is, so it should be sort of close to the verifying observation. But there is, of course, a whole bunch of different measures that expresses this closeness to the observation. And at the bottom here, I have just listed a few common so-called scoring functions. I've listed the squared error, the absolute error, which are very common, but also commonly used for positive quantities are the absolute percentage error and the relative error. And those would sort of take into account the idea that for a positive quantity, we often expect that the error grows with the level of the observation or of the forecast. And then we want to take this into account, and so we divide by either the observation or by the forecast to take this relation between error and level into account. So as I said, there's these two questions here. What functional of our predictive distribution should we report, and what is a reasonable scoring function to use? And there is a paper by Igniting, which tells us that there's no clear answer to those two questions here. There's no such a thing as a best scoring function or a best functional. But the important message of this paper is that in these two questions, there's sort of only one degree of freedom. So these two questions are really linked to each other, and that should be taken into account. So the point of view that we should take here is that either we should specify a scoring function a priori, and then if this has been fixed, the point prediction that we should issue should be done according to the base rule. So once the scoring function has been fixed, the point prediction should be such that we minimize the expected score of this point prediction. Or the other alternative is if somebody already tells us that he wants a certain functional, so he or she absolutely want the mean or the median as a point prediction, then we should insist that a scoring function is used that is consistent with this functional. And you already know some of these examples of consistent pairs of functionals and scoring functions. So you know, for example, that the mean of a distribution is the functional that minimizes the squared error. And the median is the functional that minimizes the absolute error. And more general quantiles minimize the asymmetric piecewise linear scoring function. And there's a whole lot of these relations. And the message of this paper by Igniting is really we should be aware of these pairs, and we should do our evaluation in a consistent way. And I want to show you an example of what can happen, or of surprising things that can happen if we do not take these relations into account. We might sometimes be surprised what happens. So this is again in this picture my example from above with my predictive Fréchet distributions with model 2. And as expected, you see there's mostly the seasonal trend. So we didn't expect them to be particularly good distributions. And I've plotted here the mean and the median, which we are going to use as one step ahead point predictions for our SO2 levels. And as expected, since we have a very skewed distribution, the mean is much higher than the median distribution. And to make things more interesting, I add two other forecasters. Again, admittedly, my forecasts are not going to be very good, but I want to have some competition with two forecasters that are definitely even more stupid than I am. And I call them the panic monger and the trivializer. The panic monger is this guy up here, and he always predicts a record level of SO2 concentrations. And we would probably expect that this guy is doing much worse than I am. And down here is what I call the trivializer. This forecaster always issues extremely low SO2 concentrations. And we would expect that even if my predictions are not too good, they should always be better than what those two forecasters produce. Now let's just throw those scoring functions from above on these different predictions and see what happens. First of all, if you look at those four values here, you would see that this confirms what I've said above. If the root mean squared error is our chosen scoring function, then issuing the mean as a point forecast gives the best score overall. And if the mean absolute error is our scoring function of choice, then issuing the median is more appropriate. But now there's some other surprising things happening here. So if we use this mean absolute percentage error, then this crazy trivializer wins our forecast contest. So under the mean absolute percentage error, he is considered the best forecasters of all. And if we use the mean relative error, well, the mean forecaster using my Fréchet distribution is the best. But you can see that the panic monger, the guy who always predicts record SO2 levels, is considered a better forecaster than the median forecaster. And this is sort of surprising, because looking at these pictures, we would totally not expect that those two extreme forecasters do a good job. Now, what does that mean? it does not mean that the mean absolute percentage error and the mean relative error are something completely pointless. It only tells us to be very careful and to really think a lot about whether this is really what we want, whether those scoring functions really emphasize the aspect of the distribution that we have in mind. And if we do think that those are the right scoring functions to use, then we can still make sure that we're not beaten by the trivializer or the panic monger in the forecast contest, but then we just need other functionals. So for those two examples, the mean absolute percentage error and the mean relative error, functionals that are special cases of the so-called beta median would be the optimal predictions. So using the beta median of the Frichet as predictive distributions would then make sure that again my Frichet distribution attains the best scores overall. So this is just a warning. And the message here is think carefully what you want to use as your scoring function, and make sure that the functional that you report is consistent with this scoring function. And here's already my intermediate summary, because I wasn't sure how far I will get. So just to wrap up what I said so far, we think that statistical methods are very useful because they always give us some notion of uncertainty that comes with predictions, and that's why we think that predictions should always be viewed as probabilistic forecasts, as distributional forecasts. And a good distributional forecast should have maximum sharpness subject to calibration. And I've presented a couple of very simple, but in my opinion, very useful tools to check calibration and sharpness. And I've also presented these proper scoring rules that permit us to compare different forecasters or different methods with respect to their ability to produce good probabilistic forecasts. And finally, keep in mind that when you're issuing point forecasts, you should make sure that the way you choose the functionals that you report is consistent with the scoring function that you use to assess the quality of the forecast. I've got a few more minutes, and so I want to go on to at least one more topic that I find important, and this is the verification of extreme events. In all the forecasting that takes place in practice, like weather forecasting, flood forecasting, but also in economic contexts, the focus is usually on the high impact events. People do not care so much if we predict a precipitation amount for Denver tomorrow of 10 millimeters, and then only 8 millimeters happen. That's not really what people care so much about. But if there's a flash flood and we fail to predict it, then people will get angry. And here I've just put together a few quotes, and those are taken from a master thesis by Sebastian Lerch, and you can find much more examples there. How the media and public opinion focuses on those extreme events. So this is something that we have to deal with. Now, how do we evaluate predictive performance focusing on those extreme events and giving less focus to this mass of forecasts that we issue, but people do not care so much about? The obvious strategy seems to just take those extreme cases and proceed with our methodology in the same way as I've shown you so far. So we would just discard all the non-extreme cases and then use our proper scoring rules on those extreme on those days where extreme things happened, and use them to assess performance. And people have done that actually. So here at the bottom, I'm quoting a paper, I think, from the economics literature, where people have followed exactly this guideline and used this score, which is sort of a restricted version of the logarithmic score. So this is the logarithmic score, but restricted to those cases where the observation exceeded a certain threshold. And it turns out that proceeding this way is leading to misguided inference and is not an appropriate way of evaluating predictive performance. And why this is so becomes clear from the paper by Knighting and Ranjan, who study more generally the scoring functions that are just weighted by a function of the observation. So in the preceding example, the weight would just be 0 weight for everything non-extreme and weight 1 for everything that exceeds a certain threshold. And in this paper, they show that if the observation or if the true appropriate predictive distribution is would be f, then under this particular scoring function, the best score would be achieved by a predictive density of that form. So in the special case where our weight is just a restriction to the extreme values, this density G would essentially be a truncated distribution. So if we think that the normal distribution would be adequate, then the best scores would be attained by using a truncated normal distribution that truncates our true belief at this threshold level y is 0. And this means that the score is improper. It means that we would be encouraged to only predict extreme things. We don't get rewarded for predicting anything non-extreme. And so dishonest forecasting is encouraged, exaggeration is encouraged. And very unfortunately, this is what really happens also in the forecast evaluation that is done like by the media and by the public. And this is why very often people that like to predict extreme scenarios and horror scenarios get rewarded. If you step up and predict a financial crisis every year, and then you're lucky and you get the financial crisis in 1 year, then it would often happen that people say, okay, you're the guy that predicted it, and this is sort of unfair. And on this slide, you can see the mathematical reason why this is unfair. But still, it is natural that people are interested in extreme events. So how should we proceed? What would be a fair way of putting focus on extreme events without encouraging exaggeration? And here's a few examples of strictly proper scoring rules that do achieve this. And again, you realize some connection with what you already know from estimation theory. So when you estimate parameters, you know what to do. You also know that you cannot just restrict if you have censored data, but you know, if you look here at the second example, at the censored likelihood score, this is what you would do in estimation theory. You would take into account the weighting function, and if the weighting function is again a restriction to everything above a certain level, then you can take this into account and make sure that you still end up with a proper score. And there's other examples like this conditional likelihood score, and also the CRPS has a generalization that permits you to put weight on the more extreme events, but still makes sure that your final score is proper and you do not encourage exaggeration or dishonest predictions. And those are just a few examples, and this has all been studied more intensively in this diploma thesis. So this is where you can look up more results about how to evaluate the predictive performance with focus on extreme scenarios. So here's just some final slides, and I take a look at the time, and I see that I should end quickly. So this is essentially just some advertisement for some papers. So if you found this probabilistic forecasting theory interesting for you, you may just want to look at those papers to get more detailed information. Here I just briefly mention this issue of multivariate quantities that have been of a lot of interest. So we think about looking at different quantities at the same time, or spatiotemporal things, or even fancier things like vector valued spatiotemporal quantities. And then the question is, how can we evaluate those quantities? Because everything I've said so far is applicable to scalar values. And I just mentioned a few papers here where generalizations of this PIT histogram have been proposed that permit to study multivariate quantities. Of course, the interpretation is more difficult, and of course, it happens that we lose information because multivariate quantities have a high number of degrees of freedom, and condensing them into univariate quantities implies some loss of information, but we can still learn interesting things also in this multivariate context. And there's also scoring rules. There's generalizations of the CRPS. There's this obvious generalization of the logarithmic score. And I just want to leave it with that. And if you find this relevant for your work, I would encourage you to just take a look at this list of publications that I've put here at the end. This is where you can find all the information that I've tried to condense into one talk. For now, thank you for your attention, and I'm happy to take questions.
Thank you, Michael. That was wonderful. Yeah, so I do have the ability to try an experiment today, which is if you want to ask a question, the way to do it, and this is an experiment here, you need to click on the microphone button at the top of the menu bar, and then we'll ask you permissions to accept the microphone, and we'll see if that works. If it doesn't, we'll just go back to the traditional way of the chat. There we go.
Can you hear me?
First successful.
Yeah. It's Michael from Chicago. Thanks for the talk. I was wondering, for calibration, seems to me in some cases you would want to condition on certain relevant subsets. That is, being marginally calibrated may not be sufficient. You want to be calibrated at times of high volatility separately from times of low volatility, or you want to be calibrated separately across all seasons and not just marginally across the year. Could you say something about that issue and how you think it should be addressed?
That's a good question. I'm afraid I can only give like a negative answer or a warning. So what is definitely very dangerous is to use these tools like the PIT histogram to stratify data. Then you would run into similar issues as the one that I've just talked about in the context of extreme. So applying the PIT histogram only to cases where you know that the observation assumed like a very high value or a value in a certain interval, this is something dangerous. I must admit, at this point, I'm not entirely sure what the way out of this is. If I remember correctly, then conditioning on the forecast is sort of okay, but conditioning on the outcome is something really problematic. And unfortunately, I'm not sure if tools have been developed that can do this and remain in a mathematically rigorous and acceptable framework. I'm afraid I have to.
Yeah, you definitely only want to condition on things that you have observed up until the time of your forecast. So anything up to the present you could use to condition on. So in a stock market situation where you have stochastic volatility, you know when you're in high volatility or low volatility states, or at least you have some information about that. And you might want your forecast to be calibrated conditional on your present estimate of the volatility of the system. And so that's not an easy problem, but I think it avoids your problem if you don't want to condition on the things that you don't know. Yeah, definitely you don't want to do that.
I see. Okay. Well, I have to say, I find it a little hard to think about this specific case, and I don't want to say anything stupid. In those papers, in the literature on probabilistic forecasting, there is definitely the situation where in this more formal framework, you have a sequence of increasing sigma algebras that represent increasing information, and then it tells you how to use scores and these sort of things to also evaluate how much your increase of information is. Maybe this goes a little bit into that direction, but I'm afraid I can't directly point you to something that that answers your specific questions. I'm afraid I can't tell you one specific paper, but this is really covered.
Right, thank you. I mean, certainly it seems like there's an issue between conditioning on observations and conditioning on sets as well, the index set, like time. So I'm guessing you can split the two up. Other questions? Again, if you don't feel confident about sticking your microphone on and making it work, then you can also put a question into the text box and I will read it out. Nobody chatting. So where do you think the, I'll ask a question myself, where do you think the issues are that are different when you think multivariate instead of univariate? So what, if you had some hints for people to think about, how should they think about things differently?
The general
what would you
problem
say?
is, as I briefly mentioned, that as we talk about multivariate things, then the degrees of freedom are just exploding. So what we're usually interested in are then correlations, and other than in the modeling stage, where we usually make assumptions like things are stationary and isotropic, or even if they're not, we have like a specific idea of how things should behave. In a verification setup, we would not like to make any a priori assumptions unless we're completely sure about. So that means we have to deal with a very high number of degrees of freedom as the dimension increases. And the general problem is that in order to display something graphically or to condense something into a single score, there is this big information loss. So my personal conclusion about this, I've done a little bit of work on that, is that there is, especially in the multivariate setting, there is not a single score or a single tool that you want to look at, but because of this information loss, you really want to compare a lot of different graphics, a lot of different measures, because they would all focus on different aspects. So one would still focus more on the marginal distributions, another one would focus on the correlations, but maybe mix up correlations with inappropriate uncertainty representation and so on. So you want to compare and want to use different tools to come to a conclusion, and the evaluation generally gets more complicated. And this is also an active area of research. At this point, I wouldn't say that there's the answer or the big tool to do multivariate verification. This is something very recent. Most of the literature has really focused on scalar quantities.
Wonderful, thank you. Other questions? Don't be shy. No, it looks like it's all quiet. Okay, well, I'll take the opportunity to thank you on behalf of everyone else. I'll give you a little clap. So thanks a lot for giving this talk. There's some claps going on in the windows as well. It's a little indirect, but you can see it. Thanks for everyone for turning up. Remember, this is the Statmos online seminar. If you want more details about Statmos, go to statmos.uw.edu, and certainly if you want to think about a visit, have a look at the website and you'll find further details there. Our November seminar is still to be confirmed. I've had a yes, but I haven't got further details, so I'll just make sure of that before I post anything. Our December seminar is already set, and that will be Monse Fuentes. The other thing I'm going to point out is that it's getting harder now that we're in term time to make the seminar always being at the same time at the same day. So I'm typically making it 11 a.m. Eastern, but the day is moving around, and I'm sorry if that's a hassle for you, but that way we can kind of make sure that at least the speaker can get there. So thanks again, Michael,
Thank you for
and
giving me the
I'll speak to you all soon. Okay,
have a good day.
bye-bye.
Thank you.